Hi, my name is Brooke. Today we are going to have some fun with the design of algorithms. The old Win32 was a good environment for developing algorithms, but with the advent of Win64, it became much more fun, as you have many more registers to design with. While there are many complex designs that are needed for many specialized tasks, a vast amount of code is much simpler and highly useful for doing all of those ordinary tasks that a modern 64-bit application requires. Our test algorithm is a very simple fill algorithm that is used to fill a buffer with whatever character you require, zero fill, space fill or any other single character. The algorithm, in its high-level form, starts with a normal argument list. It preserves the RDI register and the R11 register, then load the fill character from the argument list into the R10 register. The byte portion of the R10 register, R10B, is loaded into the AL byte register, and the buffer address is loaded into the RDI register. The byte count is loaded into the RCX register, and the prefixed combination of rep store byte copies the AL register content into the buffer passed to the procedure. When this is finished, the RDI register is restored by copying the R11 register back into the RDI register. This algorithm is both fast and flexible. Its results are byte perfect, and it is reasonably fast, but it can be improved by some manual optimization. Here it helps to disassemble the code to see what the full high-level algorithm looks like. By using an argument list, the passed arguments are written to shadow space, which is 3 memory writes. There are a further 3 memory writes that can be easily optimized, as the 3 original arguments passed in registers, RCX, RDX and R8, have not been overwritten. The first optimization is to directly load the registers, where they are required, to set up the rep store byte code. Doing this removes 3 memory reads, which reduces the overhead of the entire algorithm. Now when you look at the disassembly, you will see that the code to set up the rep store byte is far more compact and is also far more efficient, but the algorithm still has the shadow space overhead, which is less than optimal. The solution is to remove the stack frame, as it serves no purpose with the 3 registers, RCX, RDX and R8 being directly loaded. With the stack frame removed, the algorithm is much smaller, and with a lower instruction count than either of the stack frame versions. The rep store byte code does not get any faster, as it is already a special case circuitry optimization done at the CPU level, but with all of the memory reads reduced, the attack is faster, which means it starts and finishes faster, and there are many applications where this is useful. Now that we have the basics of at least one form of optimization working, we can do some more on an extremely simple string length algorithm, as it serves to demonstrate another aspect of manual optimization. It has been chosen because it has a 3-instruction loop code that suffers unusual overhead due to it being so short. Written with a standard stack frame, you have a memory access that is slower than using a register, and the conditional jump that loops back to the label takes up 1/3 of the instruction count. The first is simple to fix: remove the stack frame to reduce the entry and exit overhead. Addressing the second involves experimenting with a traditional technique, unrolling the loop code. Unrolling works on the assumption that a jump not taken is faster than a jump that is taken, and this has held true over many generations of x86 CPUs, as well as current x64 hardware. With an unrolled loop, each jump not taken is a fall through, and only when you get to the end of the unrolled loop is a jump that is usually taken, if the exit loop condition is not met. Now be aware that unrolling a loop does not always make the loop faster. Normally what you do is start with an unroll by 1, then time it. Often it will be slower than the single loop. Then try 2 or 3 times unrolls while timing the loop to see if it's faster. If you get a speed increase, keep increasing the unroll until the loop starts to get slower again, then trim it back to where it is fastest. Note that this will of course make the code larger, but in most instances the size increase does not matter. Algorithms of this type are that small that changes often fit into the padding after each procedure to obtain the correct alignment for the next procedure. We will do more of these in the future, but it needs to be understood that while much of computing and algorithm design is science, optimization will always be a black art that takes originality and out-of-the-box thinking. You can walk down the path that many have taken before you and get the same results, or you can learn whatever you can from any source you like, then walk your own path. The choice is yours. Keep in mind that an algorithm that you have written and understood is far more valuable to you than blindly using someone else's. If you see a good algorithm, work out how it works and rewrite your own. That's all I have for you today. Catch up with you next time.